All right, finishing up our introduction to vectors. The next part, we're talking about unit vectors. So what is, first of all, the notation for the unit vector? So our notation is the name of the vector with the little caret on top. Okay, the little caret on top indicates that you're dealing with a unit vector. So the unit vector. All right. So what is a unit vector? What is a unit vector? So a unit vector is a vector, obviously, with magnitude 1, magnitude of 1, and points in direction of original vector. Okay, so what does that look like? And I'll give you a picture so it's a little easier for those that need to visualize here. So let's say we had this vector here. So I'm going to call this vector u. I'm going to give it the name vector u. All right, and I'm going to say it is, let's say, 6 meters. So we have a direction because the arrow is pointing in the direction. All right. If I then take that vector and I shrink it back to 1 unit in length, all right, so that looks about right. So I'm just going to now move it down below. Okay, so it is in the same direction as u. So I'll put theta in. So it's in the same direction, but now it's only 1 meter. So it is in the same direction, but the magnitude's 1. So we call this vector our unit vector. All right. Unit vectors are very handy, very important, and we're going to talk about how and where they come into play a little bit later on. Last thing I want to talk about, and I'm going to add a notation in here. So I'm going to put a star on it because it's pretty important. It allows us to write things a little bit more efficiently. I'm getting tired of writing magnitude. Okay. So the word magnitude in math can be replaced with vertical bars. Okay. So from the example above, could write it like this. So magnitude of 6 meters. So that's a lot of work. I want to be a little bit more efficient, so I can replace this with the magnitude of vector u, okay, equals 6 meters. So now, magnitude, I know I see those bars around vector notation, so I know, okay, we're just talking about magnitude. All right, so very important, it shortens things up. So those vertical bars replace the word magnitude, okay? So we're going to see that jumping to that notation as we go through the next couple of lessons. So please make sure that this is highlighted in the note so that when we come across it, you're not sitting there frustrated trying to figure out what that notation means. Okay, some examples. List all equal vectors in the diagram. So equal vectors. So what does that mean? Equal is equal to direction plus magnitude. Very important that both of those are true. Okay? So we are assuming this is a square, so that means that those lengths are equal, and those that remember grade 9 math, when we did the diagonals in a square, those end up being the same length. So there are quite a few possibilities here for this answer. I'll get us started. So vector AE. So I'm going to start. And remember I said the notation for vector is tail to head, and I put a harpoon on top. I have vector AE. So it's equal to AE. Has to have the same direction, has to have the same magnitude. So AE could be the same as vector EC. Those both have the same magnitude, all right, and they're pointing in the same direction. Also, if you want to be tricky about this, vector AE is equal to vector EA. Hold on a sec, don't get saying, hey, wait a minute. EA has the same magnitude, but the direction's not the same, right? Because now EA is pointing in that direction. Can I change it around? Yep. I'll put a negative in front, and all of a sudden, that means that that head would change locations, and now it's facing in the right direction. So it's the same vector, except turned around. Okay? There's a couple other combinations we could do. DE would equal EB, for example. Like I said, there's many here. I'm not going to go through all of them. What else could we do? Vector AD. So now I'm on the outside of the square. So vector AD, what is it equal to? Well, it would be equal to vector BC. Square, opposite sides are equal, and they're also parallel. All right. Now I'm going to have a couple of you. So there's a couple of examples. It says list all equal. Well, I'm not going to wait. I'm not going to spend my time doing that. Let's list. Change that word to. Well, I guess I just changed the one. Some equal vectors. You'd be here all day trying to do this. I'm going to have a couple of people who are sitting there and asking themselves, well, what happens if? Can I do this? So what happens if I go back to AD? What happens if I write AD as an expression? So this is where we're heading eventually. If you see this or you're wondering this already, excellent for you. So vector AD, so that's my red vector I've drawn here. What happens if I follow a different path? What happens if I start at A, if I go down to E, and then I come over here? I have the same result. I ended up at point D, so is that possible? And the answer is absolutely correct. You can write, and this is called adding vectors or linear combinations. We are going to get into this. I'm not going to do a ton of them, not really part of the homework. But if you see this, that's excellent. Or if you're wondering if that's possible, also excellent. I'll do one more, just to give you a feel for what's possible. So as long as you start at point A, that's the key. You got to start at point A. You got to end at point D somehow. So instead of, I'll use the green one this time. What happens if I go over to B, down to C, and then across to D? Is that the same? Absolutely. So you could say AC is equal to AB plus BC plus CD. Okay? That is a possibility. All right, really for our homework, I'm just looking for the first 4 examples or answers, but for sure those are acceptable answers as you move through the homework. All right. All right, and heading into number 5, and I believe that is the last slide here. So last example. For the given number line, state equivalent vectors. So now you're just playing with some, I'm going to play a little bit of fractions here, so don't get too scared. I'll talk you through it. All right. So, all right, let's start off with a couple of equivalent vectors. Let's start off with something simple. So let's start with AC, vector AC. So vector AC, and off to the side here, or up above, I know that the magnitude of AC is equal to 5 units, and I know because I'm doing AC, it has to be pointing to the right. So what vectors are equivalent to AC? Well, hopefully you're saying, well, vector CD has 5 units, so that would work. They're identical in size. All right, and if you want to get technical here, if I added vector AB plus BC, that would be correct as well. What happens on a test if I force you to do this one? Vector AC is equal to DE. Okay? We know they're not the same length. All right, so what we need to do is we need to multiply by some fractional value to make this work. So I know that AC is 5 units in length. All right, I need to get rid of those 5 units. I have to get it back to a unit vector. So to do that, I'm going to take the AC and I'm going to divide it by 5. Okay, I'm getting rid of that. So dividing by 5 gets me to a unit vector right there. So unit vector. So now I have right direction, but now my magnitude would be 1. Okay. Now I want, whoops, I'm doing this in the wrong, I'm messing you up. I'm doing this in the wrong order. AC to D, my fraction's on the wrong side here. So what I'm doing is I'm forcing DE to be the same length as AC. So my mistake. So we still need the unit vector, but we need to get rid of the magnitude of DE. Right now it's 7. We want to reduce it to 1. So same idea, I was looking at the wrong vector. My apologies. So we're going to take vector DE and I'm going to divide it by 7. So now DE has a length of 1 right now because I divided by 7. I want to have 5 units because that is what vector AC is. So that means I'm going to multiply it by 5. So AC is equal to 5/7 of DE. So that is your scalar multiplication on top. All right, I'll do another example here. What happens if I want you to make this expression true? What happens if I want you to make BC equal to CE? Well, the magnitude of CE is equal to 5 plus 7, it's 12 units. So I need to reduce CE down to a unit vector. So I'm going to divide CE by 12. Okay, so that reduces it down to a magnitude of 1. All right, direction still doesn't change. I need to make it the same length as BC. So BC has a magnitude of 2. So it would be 2/12, or it's 1/6 the length of CE. All right, so you use to get this to work, you reduce it to a unit vector, and then you do your scalar multiplication. All right, and that's probably going to be the hardest question. It's the hardest question for physics. It's always difficult, and it's because you're bringing those fractions in. So if you follow that process of reduce it to a unit vector and then scale it up, it helps you out. That's the homework from the workbook, 1, 2, and then 4 to 11. If you have any questions with those, let me know, and I will help you out as best I can.